Welcome everyone. My name is Angel Francisco Martinez. I'm an engineer consultant here at Microsoft, and today we're going to do a webinar on modeling TBM in soft soil. You can ask questions through the GoToMeeting menu, and in the end we'll have the Q&A session and open the model directly. So feel free to ask all the questions you have. So the objective of today's session will be to simulate the construction of a tunnel located in soft ground. We will have this tunnel modeled as having double lining support. The first will just be prefabricated segments, and the second support will also be a solid to model what would be essentially a sliding formwork. So both of our supports for the tunnel will be solids, and then we'll also model the shield of the TBM as a shell element. Here are the dimensions of the tunnel itself. It has a outside diameter of a little bit over 6 meters, and we're simulating an excavation of a 45-meter segment with about 30 precast rings. Each is about 1.5 meters thick, and we're excavating and activating or installing two sets at a time, so advancing about 3 meters per excavation. The local conditions in this case is we're simulating the main soft soil layer is basically modeled here in the brown color of the model, and the regular stiffer soil layers will be in this case the ones that are in gray. We will be simulating in terms of local conditions, the front pressure of the TBM acting as it's excavating. We'll also have radial pressure, which would be simulating the shield. And then once we get to, as it's advancing, once we get to stage 4, we'll see here these rings initially have the property of a soil condition. We will then, after they're excavating, be reactivated. We see here shown with these dots. These rings will now be activated with a different material property, in this case concrete. So in about stage 4 is when we'll start to have the installation of the first primary support rings. And then as it's advancing, for instance, the next stage, stage 5, we see we're now starting to deactivate the radial pressure, which will be sliding down with the shield, simulating the TBM. And this will continue all the way to the end. As we see here now in the final stages, both the primary and then the secondary support lining will have these change material properties. Just a quick video of what this will look like. We'll see here the excavation, the shield passing with the radial threshold, the first lining, and then the second lining being activated in the sequence. Again, I'll do play one more time. So this is what we're going to be modeling: the shell, the TBM, the first lining, and the second lining being installed. In between, there will be stages for pore pressure dissipation as well. Now, this particular analysis will have close to 40 stages. And rather than having to do one or setting up each stage manually, what's being excavated and what's being essentially installed or simulated, we don't have to do that manually stage by stage. We have this table called the structure state wizard, and it allows us, by sets that are numbered in the correct order, we can basically set simple rules of conditions like activate in sequence and then deactivate or remove in sequence. And this saves a lot of I guess repetitive stages or manually setting up repeated stages. And we'll look directly into how to use this in the program once we open the software itself and go through the tutorial. Now, for this particular model, we're running it as a construction stage consolidation analysis, and the drainage will be simulated by boundary conditions. So we will be selecting the layers of the soft soil and applying this draining condition, which basically setting to the pore pressure to reach 0 over time. And what we're trying to capture in this particular case, it's a tunnel in the Valley of Mexico City, the lake bed, and it's simulating what would happen to the tunnel over the next 25 years due to the overpumping of the local aquifer. So it's a slow, basically pore pressure reduction over time, and it's due to the local aquifer being drained, not so much that there's some sort of manual soil improvement of only happening at the location of the tunnel. So for this case, again, this will be a construction stage consolidation analysis, and we will be applying draining boundary conditions between layers. And we can get outputs as such, excess pore pressures, or what would be the flow rates between the layers. However, if it was a different local condition, or if you needed to have more control in the type of analysis you wanted to run, we could have also run this as a fully coupled analysis and using vertical suction drains, in which case we can specify direct locations of these drains and apply what would be boundary conditions as pressure heads for us to manually control what would be the flow rate or the drain rate in the particular layers of interest. So either or the type of analysis can be done with GTSNX, but for our case, because it's a natural, or natural, but it's a condition of the aquifer being drained, not so much the project engineers working directly to improve the soil conditions, we're modeling it as a consolidation analysis. Also, as a side note, we are not applying directly this condition of contraction on the shield of the tunnel, but it can be simulated in GTSNX. So we could simulate the volume loss around the lining of the TBM, and it can be done for a 2D or a 3D model using basically the volume loss contraction ratio by the following equations. So here's a quick example, and we can also share these models with you beyond what the model we're going to cover next. But we can apply this condition, and you can see here the before and after results for the soil displacements, as well as the distribution of the forces on the lining, as well as the moments. For now, I'm going to briefly discuss the conditions of the model we're going to work in, and then I'll directly jump into opening the model and going through all the steps. So we see here we have the distribution of the soil strata. As I mentioned, the brown color assigned to these layers will constitute the clay, and we're going to use the constitutive model soft soil, seen here in the table with the darker gray in the tables. And then the rest will be just simulating regular soil, and we will use more columns. We can see this, the initials MC for more column and SS for soft soil. So that's the constitutive model we'll be working with. For more column, the nonlinear behavior will just be us defining cohesion and friction angle. However, for the soft soil, we would have to define more of the clay constitutive model. So the over-consolidation ratio, your kappa, and as well as your lambda and such. So these are the distributions, the thicknesses, or I guess the depths at the locations of each of these layers. We see here in the tunnel being located at the middle main layer. So now I'm just going to jump right into the model, open the program, and show you all the steps to go through this. And again, at the end, we'll do the Q&A. So 1 second while I open the model.
So here are the settings we're going to be working with. We set up the units for 3D and gravity in the vertical direction. And we see now the main menu open. So the first thing I'm going to do is draw a cube that will generate the whole area or volume of the terrain. The first thing it's going to ask me is the bottom left corner, or the coordinates of the bottom left corner. I'm going to type in the units for -25 in the x, 0 in the y, and -60 for the z. It's the location of the bottom left. So then my width of the x will be 50 meters, and the y will be 45, which is actually the duration as the excavation. And then the height or the depth will be 60 meters. And then I give this geometry as a name called terrain. And I say, okay. We'll see now this has generated the first geometry, and if we wanted to explore it, it would be under the set terrain. I now go to the front view, and what I'm gonna do here is draw the faces of the tunnel, as well as the primary and secondary supports. So I'll end up drawing 3 circles. I type in the coordinate for the center of the circle, which would be the coordinates 0 and then 21 for the C. As we see, we are in the CX plane, and so I'm targeting coordinates 0, 21. I can see this because that's the work grid plane I have if I spin the model. So I go back to the normal view. So we have those coordinates, and now I give it a new name to set it under the set tunnel. And I click apply. Once I click apply, it's locked in the coordination, and now I type in the diameter, or sorry, in this case the radius, which is 2.5 meters. So we have here the first drawing, which is for the main tunnel. And now I will draw this an outer circle, which is going to have the same center location. And now the radius for this one will be 2.75 meters, and this represents what would be the secondary support. So this is the thickness of what would be our secondary support, which will be a solid. And then lastly, we do the last ring, which would be the same center location. And this will be representing the primary support. So once I click apply, I type in the radius for this last circle, which would be 3.025 meters. So then when I click OK, we see the last circle appear, which represents the two rings. So right now, this is just representing drawings of 2D circles, as we see here. So in order for it to be a tunnel now, we just need to extrude it so that it can become a solid. So I want to do this in a series of stages or steps. So I'm going to first modify my filter to select the inner circle as an edge, then I select the direction, and now I'm going to give it a distance of which is going to be, in this case, 45 meters. And I'm going to save this under the group tunnel. So you see, once I apply it, I rotate the model a little bit, I can see that I extrude in this direction, and it's now a solid is under the work stream. So if I click it, I can hide it, deactivate it basically, and that makes it a little easier for me to select the secondary support, which is like by selecting the next circles. So I click both of these circles now, the outer and the bottom boundary. The direction will be the same in the y direction. And I'll do this again for 45 meters. And this is now under secondary support, as I'm putting here, RS. Then we can verify here now this new solid created. So I hide this one more time, and I repeat this for the next edge. Edges, actually, I'm selecting the two outer edges to represent the primary support, again in the y direction, and a distance of 45 meters. This will be the primary support. And now we click and apply. And so we see here now we have created the two supports plus the tunnel cylinder that will be excavated. As I click them here in the workspace, so you can unhide them or activate them again. And now show my front view. Again, the front view in this case is the CX plane. And what I'm going to do now is generate a surface in order to divide this tunnel into the stages of excavation, or the distances of excavation. So I draw a rectangle just big enough to capture the volume of, or the face of the tunnels. We see here now from the isometric view that you start to get the picture. This surface, if we make copies of it, we can then use it to divide these solids. So I'm going to use the command translate, select the direction, and I'm going to make either move it or I can make copies. So since I have a pretty uniform distance, I can just use the command for copy uniform. And so I just tell it I'm going to be advancing at 1.5 meters 29 times. And if I do the preview command, we can verify this distribution. So if I click OK, then we see that we've now generated these copies, and this is basically telling us the spacing of where the tunnel sections are going to be. As we see here, by clicking on one of them now, it's still connected or still considered a single solid. But after we divide it, we'll have the individual sections. So I use the command, what would be for selecting all three solids that we're going to divide. So those are our target solids. And then now I go back to the front view so we can select the surfaces that will be the dividing tool surfaces. So I can either click one by one using the normal click, or I can modify the selection filter and use this intersect command that we have, that anything that's intersected in that plane, in this case all these faces, are automatically selected. So we have these 30 faces selected, and we said divide the solids, so now I click OK. And we see here now we have divided, and if I put my mouse cursor over it, we can see that it's now been divided. And it's divided all three of the solids, the rings, as well as the inner tunnel. If I go back to my regular selection filter, I can individually click on that, and we see there that I have three solids for each sections. So I turn the terrain back on, and now we need to divide the solid by the strata layers, and we can also see that these solids are still independent of each other. If I hide the tunnels, you can see that the cube itself is not represented a connected tunnel. So we're going to have to account for that as well. But what I first want to do is generate the surfaces to divide my strata layers. So I'm going to modify my work plane location. I now use that reference plane command to switch it into the y-x plane. So when I click now to do a normal view of the work plane, it takes me to the top. So I'm going to do a similar step and draw a rectangle just big enough, or bigger than the solid, as we're going to use it to divide. And again, we're going to make copies of this surface. This case, however, now it's going to be in the C direction. And now it's going to be non-uniform copies. Each of these strata layers have a different depth or thickness, so we just type them in directly under here. So we see here the first one is at 3.5, the next one is at 6.5, and then so on. The next one would be at -1 meter for the next one. After that, it's 26.5. Then we have another 3, and then followed by the last one, the 12. And so we click the previews, and we can see here, these are basically our strata layers. So we can click OK. And so now we repeat the steps as when we divided the tunnel. We end up going to divide. We select the solid cube. And then again, we modify our selection filter so that in one command we can select our surface tools by intersecting them. We have 7 of those. And now we click OK, and we see we divided up the solids. So the last thing we'd have to do now is we can see, again, verify that these are not connected. So we need to use the command autoconnect under the Boolean method, and it's actually easy just to select everything. And this will connect it all. So we see here now, after the autoconnect command, if I hide the geometries of the tunnels, the terrain is actually accounting for those solids as being connected, not overlapping anymore. So I can kind of deactivate them and deactivate them here in the workspace, and we can see that. So we're done with the geometry, and now we're ready to go to the mesh. And in order for that to work, we have to define the materials. So here is where we can select our constitutive models. We see the list we have here. So we would be defining the following tabs. The nonlinear behavior for more column we see is the following, and depending on which is we're using, we're also going to be using soft soil. And so these are the values we would be typing in. The two main ones we're going to be using. Subsoil for would be the clay, and then more column for our regular soil. And then we're also going to be using elastic with a structure option for our concrete and our shield materials. So I could either type in manually, but to save a little time in this example, I can also just import the properties with the assigned materials to them. So because here we see that it was where we define the properties, so we would be able to do the materials here. So for instance, the only things that would be 2D in our case would be the shell, which is the shield, whereas all of the other materials would be 3D. So we can actually import this from a finished model, just to save a little time, and we see here that we have all our soil layers as well as the concrete. And so we have all the solids, and then lastly the shell. Here are like our different layers. They're all 3D. The concrete and then the shield. And this imported the materials, as we see here, which considered model is assigned to each of the soil layers. So we see we have these four with more column for the more rigid terrains, and then for the clays we're using soft soil, as well as the concrete and the shield for elastic. So now we can actually go into the meshing. And it's a good tip to start from what would be from in to out, in which the outwards, what would be like the smaller meshes. So here, I'm gonna first start with the tunnel, the innermost part, and I drew a little line, again with the intersect filter to select them all, and now I give it a size. It's gonna be a 0.5 meter, and I'm gonna select either tetra or hybrid mesh. Hybrid is a combination of elements with cube and pyramid, so let's do the hybrid. And so since this tunnel now is in the layer FAS2, this is the material I'm going to assign to it. So then I give it a name, and this would be tunnel, and I click apply, so it's going to mesh them all in parallel. And so let's see if we can inspect this a little bit. And now I zoom in a little bit, and I'm going to repeat that process for the secondary support. Again, we see the 30 geometries, the same material property, same size, and now I just changed the name to this one to be secondary support. And then we repeat the process for the primary support, the outermost ring, and it's everything the same, except this time it's primary support for the mesh side. And we are now done with the tunnels, and so we can start meshing our soil layers. So I'm gonna modify or go back to my regular select filter. This layer is gonna be 2 meters. This is our primary layer. And we click OK. So to save a little time, I'm actually just gonna open a model to save a little time that's already meshed. And we see here I have the sets shown by material properties in different colors, hence why the tunnels are the same color as this layer. And so these are matching what are in our table from the PDF tutorial. So once we finish our 3D mesh, we can now go and generate the mesh for the shield. And so to do that, we are gonna actually just do it by selecting the faces of the geometry. It's a lot faster than selecting the meshes. So I activate the outermost tunnel or rings, which is the primary support, and then I use the command extract. And I select the faces that are corresponding to the outermost face. So we see here these are the, clicking on them is one way to manually select them. An alternative way is I can select this other filter that we have, which is like a polyline selection. And with this one, I can generate a series of polygons and then close it off to make an irregular area. And whatever is selected under these will be captured. So we see here that if I carefully make a volume or an area for these outer rings, it captures everything under that direction. So we would have to repeat that step for all the other outer sections, and then just assign the shield material property to the 2D shell. But again, to save a little time, we have already done that step for the whole outer face. So I can just show you here in the worktree wherever this corresponds to. If I activate them here, we see this, the 2D shell of the shield. And it's matching all in color because it has the same property, but I can actually also visualize this as a mesh set with the different colors. And we see now where each of these are individuals. They're each about 3 meters in thickness for these rings. So now we're going to move on to apply what would be the pressure loads. We'll start by first applying the front pressure load. And so for that, we're going to apply that pressure load to both the parts that will be tunnels as well as the support rings. So I'm going to activate those sets. So we see here we have the primary, secondary, and tunnel mesh sets. And so we see that these are sets are going to be activated in a sequence. And we're going to simulate the advancement of the TBM of every 3 meters. So we're going to do every other set as simulating where the load is going to be applied. And so I'm going to do my side view and modify the selection filter to intersect. And I'm going to draw these series of diagrams to deactivate basically alternative one, basically leaving one on and one off to simulate what's like the advancement of 3 meters each. And so once selected, I can do a right click and do hide, and we see how here we've basically made it easy for us to select the faces of the sets that we want to apply the load to. I now go to load pressure, and if I do a rectangle only to the left, we'll select the faces of only those elements, and I can directly apply the pressure load of 265 kilopascals. And this is the front load 1. And we see that generated there for that first step. And so we repeat to the next one. We select the new faces, and this would be my next front load. And I assign a corresponding increment number. And in this repeating process, that's how I would go about repeating this for the rest of them. So again, we've already done this for the rest of the model, so I'm going to skip ahead and move on to apply the next load, which is the radial pressure. This might actually be a little easier to do on the geometry. So I'm going to now select, instead of selection type, would be faces. And I can select my outer faces of the rings. So since we are advancing 3 meters each time, again, we select 2 rings for time, 8 faces total. And we have selected all the outer perimeter. And now we apply again this radial pressure load of 265 pascals, and this is under the radial load. And then we would be repeating this process for each of the sets as we're simulating the advancement of the TBM. And so we would repeat this process and give it like an incrementing name, in this case radial 1, and so on and so forth, until we get to the end. But again, to save a little time, I'll just open a model where all these loads have been applied. So here we're inspecting the one with the pressure loads already activated to the front as the face of the TBM. And then I'll now show you how these loads look assigned to the radial loads assigned to the solids. So we see here we are now done with applying what are the loads. So we have the front, and in this case we see here these are the radial loads that we're calling them basically shield. And again, verifying that they're advancing at a span of 3 meters, basically 2 rings. So now the next thing is basically the behavior that we're capturing for the tunnel support. As we recall, we've initially meshed it with solid properties, but now we're going to use those same mesh sets later as the supports. And that basically means that that same mesh set is going to first be ground, and then it's going to be concrete. And so in order to do that, we're going to use a command called change property, since here. And so what this allows me to do is that this one mesh set is going to have different properties at different stages in the analysis or in different stages in the project. And so we want to do this for the primary and secondary supports. What we also need to do is also organize the basically order of our supports. And for that, actually we should do this first before changing the properties so it's organized. So what we want to do is use this command called meshset rename. And so what this allows me to do is, for instance, select my sets. If I again do a quick intersection of my mesh sets in this axis, it selects all 30. What I wanted to do is use the basically sorting order in the direction of excavation, which is the Y, and to be incrementing, since we're in this model excavating from left to right. And so we give it then a name, and the program is going to start with the suffix number we gave it, and then do an increment. So we see here now that it's organized now from 1 to 30, and I'm going to tell it to sort it for me by name so that it's organized. And so now I go back and activate the tunnels. So we would see that it's now in order. See, as I'm selecting it, it's now incrementing in the right direction. And so we did the same process, although I'm not showing it, but for the primary and secondary supports. So they're all now organized in sequence using the same command. So we see here activating 1 and activating 2 and 3. It's now incrementing or activating from left to right. And so I can turn them all on. And we see here, this is the primary support, or the secondary support solids. Going to make it a little more clear, I'll reactivate the view by mesh set colors. And then here we see now the primary supports. assign, just verifying them, activate them. So the whole point of organizing this is, we'll see later, is for our construction stage wizard to be able to properly take advantage of the table format in order to set up the stages, and for that it needs them to be already have a number in the correct sequence assigned to them. Okay, so now we can go and change our property to the supports. And so we would be doing them in sequence. See here, I'm first selecting the first two support, the primary support rings, and I'm changing that to concrete. And we see here now we have these icons showing that it's been now has a boundary condition for this new material. So I repeat this for the next two sets of rings, and I give this the primary support too, since these are going to be activated together. And so we would repeat this for every two rings, doing this change property boundary condition. And then we would repeat the same process for what would be the secondary support. Here I'm hiding the primary support rings, and then we would go and do the same, selecting again in sets of two, and we give it a name. In this case, we assign the concrete material, and then this is the secondary support. And so since they're applied together or activated together, they're selected together, and then we do the next one, R2, and so on and so forth. So we would do this to finish the rest of the support rings. And again, I'm going to go ahead and just open another model that I've already done this for to save some time. So we see here now we've done this for the primary supports applied to the 15 stages. And then we have it here for the secondary support as well. So just to show you again, like this represents the primary support, and it's applied to the first two rings. So now I'm going to go back and activate all the mesh sets. And so now we are going to apply the rest of the boundary conditions. So we will go to boundary constraints, and we select the option auto, and we do boundaries, and we click OK. So now we see here we have these icons displacing for these boundaries in the y direction, and then in the bottom fixing what would be movement or displacements in the x, y, z, which is basically simulating the contact with bedrock. And so it's actually kind of easy to see based on the icons which direction it's fixing the movement for. The other thing we need to do is apply a gravity load or a self-weight load, and we just verify that it's doing it in the negative z direction for gravity. And so this would be self-weight. We see there the arrow. And then the last thing we need to do now is apply the consolidation boundary conditions, which would be for draining. And so it's actually a little easier to do this applying it to the geometries. So I'm gonna hide the mesh sets and turn the volumes of the terrain on. We have our 7 soil layers here. And so I'm gonna apply this boundary condition called drain, and I'm gonna change the selection filter to be face. And I can select the outer faces of the layers, of the regular soil layers, not the clay layers, where we are going to apply the drain condition. We call this the draining strata. And then the last thing we have to do is define the isometric validation. If in this particular project, what we are going to do is we're going to reduce the pore water pressure by increments of 20%. And so for that, we're going to use a function that's called, in this case, the non-hydrostatic water pressure. What we need to define are the locations by XY coordinates, the top and bottom elevations with the C top, C bottom, and then the pressure at the top and the pressure at the bottom. We see here then the coordinates related to the Excel table that we have this data in. So at the top, the pressure we're going to be considering is basically the water level being completely at the surface. So at the top, it's going to be 0 for pore water pressure. And then after, at the bottom, we're going to give the value of 480 kilonewton meters for what would be at the end of that stage. It should be the pressure at the bottom of the model. And so we see here then we will be assigning these to the same mesh sets, but as we see, the bottom pressure is going to be the one that's going to be decreasing. So again, we have this in an Excel table, and so we can just directly copy paste this from the table, and these values correspond to the coordinate locations, with the C being 0 at the top and negative 60 at the bottom, and then the pressure at the top being 0, and again, the pressure at the bottom for this, for the 20% pore pressure reduction will be 480. And we will repeat this process until we get to 100% pore pressure reduction, which would be basically both pressures at 0. Again, we can do this as just copy pasting here. So function, for instance, function 1, I just bring this from Excel, Control C, Control paste. So this would be the function 1, and I apply, and then I repeat the same process, function 2, function 3, and such. And so we can verify this under the workstream analysis tab, and then we see here we have the functions. We can expand, and we would be able to see this non-hydrostatic pressure. We need to modify it. We can just right-click it to edit. So we did this 5 times, 1 for each of the soil layers. So I'll just go ahead and skip into another model where I've already done this. And we can inspect that here. When we reach the 100% pore pressure reduction, and we see that both the pressure at the top and the pressure at the bottom are 0. So this is the worst case scenario for this particular project, in which the whole pore water pressure has been pumped out. So here I'm just giving a quick inspection to everything activated. We see the represented loads, boundary conditions, and change of material properties. So we're basically done with the model. So now I have to define the construction stage analysis, for which we have a wizard for this. And again, this wizard can be taken advantage of so long as like the sequence of these tunnels and excavations or whatever is in the right order. So we can just go to the wizard under the static slope analysis. We see here construction stage wizard. So this wizard has here a column of everything they've organized as everything we've done in terms of the mesh sets, the loads, and the boundary conditions. And so we would all we need to do now is create depending on the type of analysis we're going to do, a construction stage set. And then we'll be able to use this wizard. So I go here to the analysis tab, right-click at construction stage, and we select the type of analysis we're going to do in stages. We see here a full list, and we can do seepage stress, coupled, even heat transfer now. In our case, we're going to do just consolidation stage analysis. And so this is going to be, we give it a name, TBM. I'm just going to select this and show you what it looks like if we were to do this manually. We we see here we have the first step of everything we made. We would drag and drop into the middle of in the middle of each window, either activate or deactivate our sets. And then when we're done with this stage, we're just able to go to the new one. But since our model has a lot of repetitive stages, this might be tedious, and it's actually ideal for our stage wizard setup. So now that we made the construction stage set, we save that as TBM, we can now select and save that into it. So what we're going to do is we select first what we're going to be doing. So let's start with the mesh sets. And then we're going to tell the program what we want to either activate or deactivate. So let's say, for instance, we want to activate or remove the primary support. So we select RP and then stage primary support, and then we do the R for remove, and then we tell it to do it every 2 stages starting at stage 1. And then we repeat that step for what would be the other, since we're doing it, I guess, 2 at a time, we're doing what would be starting at stage 1 and starting at stage 2 for the name. So this is for removing or excavating the primary support. And then we will repeat the steps for the secondary support. So as we said, we select R to remove. We're telling it to start with the postfix, basically with whatever has the name 1 or 2. And to do it every 2 stages. So this is why because we have 2 rings together at being activated and deactivated in the same stages, this is why we give it the 1 and the 2 for each. And so we have to repeat this for the 2 sets. For the tunnel, we named that excavation, again remove, starting with excavation number 1, and then to do the same thing for the ones that have basically started with excavation number 2. And to do it every two stages. So we can also do this now for activating. So considering that we're also going to have a shield activated, and it's going to be every 2 stages. And again, we do this 2 times, starting with name 1 and 2, and it's going to be every 2 stages. So this is the TBM shield. And we would do the same kind of distribution for loads. So for instance, the load set for the shield, starting in stage 1, incrementing stage 1. And we can do the same thing to deactivate the set. So as the TBM is passing, this load is also going to have to be eventually deactivated. And based on our table, we know that the TBM passing is going to be, the load is not going to be acting anymore after stage 5. So this is why we're telling it to start to remove it after stage 5. And then if we apply the rest of the rules that we have in the tutorial table and just click apply, we would see this here transferred into this table information. And so we can verify more or less what we're doing. We see, for instance, the mesh set shield versus mesh set load. So for instance, here we're first excavating the shields, as well as the support rings. They're going to be initially excavated. So again, we would basically do this for the rest of the stages, but to save a little time, I'm just going to open one where it's completed. Basically all the information that we have in the table from the PDF tutorial. And I'll open up the wizard and show you now. This is basically when all the stages have been typed in and the rules have been applied. And so we can see here for all like the activation and deactivations of the tunnels, the shields, even like the boundary conditions represent the changing of the support materials. So even when the tunnel is first excavated and then when the support systems are reactivated, recalling that we now assigned it a different material property. So stages S20 and S36 don't have anything activated or deactivated. These are the stages where we give it for pore pressure dissipation between the finishing of the excavation and then the finishing of the primary support being installed, and then the secondary support. So we can verify everything that the tunnel wizard has generated for us if we now go back to the analysis tab under construction stages, and we see here that we have all of our 41 stages. And then we manually added 5 more stages to model what would be the pore pressure reduction long-term of a project after the tunnel is completed. And all we're doing is applying those boundary conditions that we copy-pasted from Excel, and then we assign a duration for each. What we also need to do for the wizard that cannot be done in the, for the construction stages that cannot be done in the wizard is define or verify that everything is activated, but also define the water levels. So the water levels are going to be at the surface relative to the origin. So this is where the value is 0. And for consolidation analysis, we're basically defining the duration of each stage. And for our case, we're just basically going to be modeling each excavation with the duration of 1 day. So we just basically verify this. And we would have to basically just go through this for each stage. And then when we get to stage 4, I'm actually doing here a clear displacement, basically restarting displacements. And this is because we can't really simulate the influence of the TBM for the first few stages, as it's basically not realistic, the behavior that it's going to give us as it's coming in to the front of the model. So we give it up to 4 stages, and this is where we start to see now the real displacement results. And so we're basically considering what's happening in the middle of the model, and hence there at stage 4. And then at the end, also applying what would be the boundary conditions and the water levels. We would have to use it for the pore pressure reduction, use the function for water level mesh sets. And we would apply, or you do the selection of these water level conditions when the option use your water define. And we basically have to do this for each of the soil layers. So we see here we have our 7 soil layers, and we apply them for each stage. And then we would repeat this for the 40% for all the soil layers. They each have their own function assigned to them. And then all the way to the end. And so we're actually done setting up the model. And the last thing we need to do is just create the construction stage analysis. We see, that the software does have other options and types of analysis. It could just be, if we just only wait one particular stage to do something like a slope stability or a seepage, you basically have individual analysis cases you can create. But since we're doing a construction stage analysis, we want us to do the solution type construction stage, and we would just select the set from the menu, since we only have one. And then now we go to analysis control. We want to consider the pore water pressure, initially stresses, in this case stage 1. Consider the K-naught condition. And then other options like considering the initial configuration of the activated elements. And then in the output control, we also want to consider what would be the strains. So in this case, I already have the case ready, and so I can just go here, and again, if I needed to modify it, I can just click edit. And so then I'm ready to run the analysis. I can just right click it and go solve. So in this case, this model has I already ran it, again to save time. So I'm actually now in the post processor. Basically, I'm ready to inspect the results. Hence, why I'm in the post mode, and there's that lock. And so I can now go to the results tab. So we see here that the worksheet is organized the results for us for each stage. And as we scroll down, we can see all the outputs for all the stages, including the pore pressure reduction stages at the end. So we can start expanding these plus signs to see the types of results. For instance, we have displacement, solid stresses, solid strains. If I expand on the solid stresses, so we can first start by verifying the effective stresses. So the SCC are the vertical stresses. And we can do this by comparing the verification, which would be the effective vertical stress plus the pore pressure should be our total vertical stress, which adds up. So we're good in terms of pore pressure. And so now we can go on to the next stages to start the displacements of the excavation. I'm going to make a plane cut or a clipping plane cut so you have a better view of what's happening inside. And I'm going to put the side view. So this is the first stage excavation. And we see that there's very small displacements happening. And we see that due to the pressure of the TBM, we do have some of the displacements going into the terrain. And again, as we would expect as well, for the excessive pore pressure, there's a reduction in the bottom of the model, which is shown in red, or the tunnel, and then increment to the top. I can now advance basically for choosing a type of result, displacements. There's a bar at the bottom that allows me to increment the steps of the analysis. So we're seeing here that there's a progression of the TBM, and we see that as the rings are supporting, there's a concentration in the middle of the model, which is basically where it's going to be the most realistic part of our analysis. As we keep advancing, we start to see the installation of the primary and then the secondary supports. So again, the middle section is the most representative of what's really happened in the project. So I actually now want to do a different cut of the plane. I'm going to now go into my Y plane, so we can kind of see the cut of the model in the front, or as it's going through. And so in this case, I'm going to be looking at the CX plane, and now I can go to the front view, and we can see the displacements. In this case, we're going to look at the displacements for stage 36, which is when we're done with the installation of the secondary support. So let's take a look at this, basically vertical displacements. And I'm going to use a probe command to basically select nodes of interest and get values directly. And then if I am to, let's say, looking at this, would be horizontal displacements, I can now either select values of interest or directly let the program use the min-max command to show me where the maximum and minimum displacements are happening. In this case, they have their same range of value. It's just depending on if it's negative or positive, depending on the angle or direction. And so now the last thing is let's verify the vertical displacements during the pore pressure reduction. Now this case was simulating what would be for conditions in the Valley of Mexico City, which is very soft clay, and there's a high settlement due to the pore pressure reduction over time. So we'll see here, I'm going to click at the top of the model and around the tunnel excavation. And change my units to meters. So we see that after 20% pore pressure reduction, there's a reduction in elevation of 4 meters. At 60%, it's 7. And as we increment, we see that once we reach 100% pore pressure reduction, we're getting a settlement of around 14 meters in the surface and close to 10 around the tunnel. Each of these stages has a time stage of 5 years and a total, basically, of all 5 of them of 25 years. So we're deciding or running the analysis here for what would be the worst case scenario and to see if the tunnel itself can hold up to the stresses. The worst case scenario of 100% pore pressure reduction. So now we can also, we just inspected the results for the soils, but we can also inspect the results for the support elements, or in this case, let's first look at the shield. So we can look, for instance, at the moments on the TBM shield by clicking here, and I can make an animation of this advancement. So we see here, this is the TBM shield advancing during the excavation, looking at the moments. But we can also do this kind of animation looking at the results for what would be the axial forces. And so lastly, what we want to see is the results for the support elements themselves, the primary and the secondary support ribs. So in order to do that, I'm going to go back to the work stream and hide all the mesh sets and only leave activated the primary and secondary supports. And now I can look at the results. Let's go for stage 19 is actually when we finish our installation of the primary support. So let's look at solid stresses. In this case, the vertical solid stresses. And so I can see this process with an animation here. The first part is being excavating, and recall reactivating them now with the concrete rings material property. And so this is the animation for the installation of the rings. So again, stage 19 is where we finish the installation of the supports. And the secondary support is finished installing in stage 36. And then all the other subsequent stages are now when we're doing the pore pressure reduction, 20, 40, 60, 80. In this case now, 100% pore pressure reduction. We notice that we have positive or red values, which is tension on the outer rings. And we see in the interface, which is blue, negative or compression stresses. Now looking at the horizontal stresses, again, for stage 19, which is where we finish the installation of the primary support. And now I'm advancing of the key to stage 35, which is where we finish installing the secondary support. And then looking at the stresses for where there's the pore pressure reduction for the 20, 40, 60, 80, and 100%. And now we see, in this case, that we have the tensions or the positive red in the inner face of the secondary support. And then we have compressions or blue negative values on the outer face of the primary support. And this is opposite to what we're seeing in the vertical stresses. So now I'm gonna do a cut of my model to look at the results. In this case, you see that we have the other cuts we did in the past, but I'm only going to activate this this new cut, and I'm going to do the front view. And I'm going to go to the total displacements for the last stage, horizontal displacements. And to make it a little easier, I'm actually going to activate vectors and showing the max and the min, what would be horizontal displacements. So we see here our displacements combined are about 6 centimeters. So we have 3 in the negative, which is left, and 3 in the positive, which is right. So around a little over 6 centimeters. For the local norm in this particular project, the admittable deformation would be 1%. Hence, if this tunnel has a 6-meter diameter and we're going displacement of over 6 centimeters, it's not passing what would be the local norm requirement of 1% of the diameter of the tunnel. So this would require additional reinforcement based on the displacements that we're seeing here. So now I'm going to go back and activate the rest of the geometries or the mesh sets, and I'm going to hide the vectors. And I'm going to make basically an extraction of data, and to do that, I want to basically select what's happening in the middle of the excavation. I do my top view, and I'm going to hide basically half of the model elements so that I can then extract the results directly from sections that are inside. So if I want the radial stresses, and I want to generate some sort of table format for that, I can use this extract results command. And from this table, I can select any type of result that I want. So let's go to select the solid stresses. And we see here it can be the vertical, or horizontal, or whichever. And then the next thing would be to select the stage, which I want to be included in the table. So I care about stage 19, which is where the primary support is finished installed. And then stage 35, which is where we finish the secondary support installation, and then the last 5 stages, which is where it's the pore pressure reduction. This is related to the order of which a table is going to be generated, and it can either be by node or by element. So we select element, and then I select element by element to the ones related to the outer. So I would go selecting around all the soil elements that are in contact with the primary and secondary support rings, or in this case the outer primary support, and then I would click on table, and we see here that we've now generated the table with the results that we want. And then from here, it's actually, we can select and directly export to Excel by right-clicking, or we can also graph internally in the program. But if we were to export to Excel, then we would be able to generate, for the vertical and in the Z, X, and Y directions, and then be able to get the polar coordinates, the polar stresses for what would be each of the stages, and then for the primary and secondary supports. And these are the tables that we would then be sending to the structural engineer. With now all this data in Excel, we would be able to generate these graphs for initial stages, and then do comparisons for the primary versus secondary support, and especially over time of the pore pressure reduction. And then the engineer from here would be able to determine if it's reasonable and if it needs to be designed, or with these data we can then design. But that's basically the conclusion of this step-by-step, and we can now go back to the presentation.
Okay, so we're done with the modeling, and now we I guess have reached the conclusion of the training itself, and we can just leave the next few minutes for answering the questions that have been made throughout the session. And so there are a few already open, and in the meantime, I'll start answering those while you have a chance to make more. So there's looking back some questions about